is something called implicit differentiation. Okay, so suppose you have a curve y equals g of x. How would you differentiate g of x squared? If I said take the derivative of g of x squared, what rule would you use? Chain rule, you're right. Okay, so it would be 2 times g of x to the first power now, right? Times the derivative of the inside function, which is g prime. Do you buy that? Okay. Okay. Replace g of x with y. Okay? Like, do that. Take that line that I wrote up there and write it below what I just said and replace every single g of x with a y. Derivative of y squared is equal to what? 2y times y prime. Does that make sense? You see how those are really the same thing? Do you at least buy that? Let's write it a different way. Let's write it that the derivative of y squared is 2y times dy dx. That's the same thing, just different notation, right? Do you buy that? Okay, so tell me, how is what because really, I mean, you buy it for this one, right? All I did was replace g of x with y, and that's what it looks like. Okay, you buy, okay, that's the point. Now, look at how that's different than the derivative with respect to x of x squared. What's that equal to? 2x. And in this case, it's actually a little bit easier to think about it in the second notation. This is dy dx, kind of like change in y over change in x, right? With this one, where the variable was x, if you applied this same sort of reasoning, you'd have a dx on the end. And that's like saying, okay, I take my change in x over the same change in x, and this thing just cancels out to 1.
dy dx means you changed all the x's with y's?
Yeah, so dy dx is dy dx is the slope of the tangent line. And that's what that means. That's what so if I were to say, be able to say solve for this expression or something, then I can find the slope of the tangent line. But the point is that you see how this is called the derivative with respect to x, or change in y over change in x. And so whenever you do a differentiating a y squared is the same as differentiating x squared, except for what's this addition? There's this additional dy dx term on the end, and that officially is the chain rule. You see what I'm saying? Because officially it's just like this thing, right? So if I said take the derivative of y cubed, what would that be? 3y squared dy dx. And it's because the change in y over change in x might not be a constant, whereas change in x over change in x is. Versus, what's the derivative of x cubed? Just 3x squared. What if I would have asked you to do this? d dy of x cubed. Do you see how this variable no longer matches that variable now? So what do you think it would be? Not 0. Because if actually you don't know x is a constant. So I mean, like usually x doesn't mean a constant, but it's like of a, then yes. But usually x is a variable. Think about how this one worked. It was 3y squared dy dx, right? This one will be 3x squared dx dy. That's just the reciprocal slope, right? It's change in x over change in y instead of change in y over change in x. So it has to do with, we're mostly going to do stuff like this, okay? That's just an example of how it would What matters is what kind of derivative you take, like with respect to what variables, what that vocabulary is for that.
What would be the normal line slope?
The normal line slope would actually have to be the negative reciprocal. So it would not quite be the normal line, but that's a guy, I had had that thought myself and then realized that no, that wasn't correct. But yeah, that's definitely close-ish. But if you differentiate, if you're taking a derivative with respect to x, you have to add on of a y, you have to do it the same way, but add on a dy dx term. You can also use y primes, okay? But we're going to use this to differentiate functions, actually differentiate equations where they're not functions, like where you can't get the y by itself. And it's called implicit differentiation, but the basic principle is that it works the same way as regular differentiation, except for you add this dy dx term whenever you differentiate a y. That's the only difference. So let's do one. Okay, that's kind of just what I just said. Okay. So if x squared plus y squared is 25, find dy dx, or the slope of the tangent line. So you're going to take the derivative of the left side, and that's going to equal the derivative of the right side. You differentiate both sides. That's what the d over dx thing means. You also could use a prime. And is differentiating sums difficult? No. So what's the derivative of x squared? 2x. What's the derivative of y squared? 2y. And because the variable is different, you have to add this dy dx. You could also add y prime, that just is the different notation. And then what's the derivative of 25? 0. Okay. So far is that okay?
Because we're ddxing.
Because we're ddxing, that's why there's the dy dx. If we were ddying, there'd be a dx dy.
Okay.
Does that make sense?
Yeah.
Yes, okay, great. So now, the question said find dy dx. Can you get dy dx alone in this expression? Subtract the 2x. So 2y dy dx equals negative 2x. Divide by 2y, right? So dy dx will be negative 2x over 2y, or negative x over y. And this is an equation that tells you the slopes of your tangent lines. It's a little bit different than the ones you've seen because most of the equations you've seen only involve x's, right? They don't involve x's and y's. Does that make sense? This one involves both x and y. So we're asked to find an equation of the tangent line at the point 3, 4. So how would you find the m? Plug 3 in for x and 4 in for y. So the m is negative 3/4. And the equation is y minus 4 equals negative 3/4 x minus 3. And I just think that you guys can arithmetic well enough that we'll just leave it like that. And let's see, and I did this example at first on purpose because it's an example for which you can say what the curve looks like, and so you can see if the equation for the slopes of tangent lines makes sense. So what does the graph of this thing look like? Its radius is 5, and it's centered at the origin, right? So out 5 in every direction. Okay. Does it make sense that in these two places, the tangent lines are horizontal? And in those two places, the coordinates are x is 0, y is 5, x is 0, y is negative 5? If you plug those numbers into this equation for the derivative, does it give you a slope of 0? It does, doesn't it? You do 0 over 5, that's 0. You do 0 over negative 5, that's 0, right? Does it also make sense that you're going to have vertical tangent lines at those points? And those points are the points 5, 0, and negative 5, 0. And if you plug them into your derivative formula, you're going to get undefined, i.e. a vertical line. So, yeah, and it's kind of crazy, but you could technically have solved this thing for y, right? Like you could have gotten the y by itself and then done the derivative. But it's easier to do it this way.
What if you have a graph that crosses the origin Wouldn't that, and there is a slope there, wouldn't that be, what, you'd get 0 over 0, wouldn't you?
It depends what the equation is. So you might not get 0 over 0 when you do the derivatives. Because like if your equation had like a, say a 5x in it or something like that, the derivative of 5x would just be 5, which would give you a constant, so that wouldn't always happen.
What if we took this circle and shifted it 5 units?
Oh, well, yeah, but then you would get the derivative being the right thing in the right place. But it, yeah, it's kind of crazy, but it does work out. Yeah, I know it's kind of weird. And one more thing I want to mention. You've technically been doing this all along, you just didn't read it. So if I gave you y equals x squared plus 1, and I said, give me the derivative, what did you say? If you were doing proper notation, what would you say on the other side of that? Y prime. Or dy dx equals 2x, right? The derivative of y is 1 dy dx. You see what I'm saying? It's kind of the same thing. Does that make sense? It's just that everything you've seen so far has been y, not y squared. Okay, so let's do another. Okay, so find dy dx by implicit differentiation. So you've got the derivative of the left side equals derivative of the right side. And because they're saying dy dx, you know, you do d over dx, not d over dy. Do you see what I'm saying? That dy over dx means the dx is in the bottom. Okay, so the left side is simple. What's the derivative of x cubed? What's the derivative of y cubed? Times your dy dx from the chain rule, right? Or y prime, whichever you want to say. Okay. Now, the right side is tricky because it's a product. So is it right to say 6 dy dx? You see how what I did there is I said, okay, the derivative of 6x is 6, derivative of y is dy dx. That's the bad product rule. Don't do the bad, that's the no product rule. That's the wrong product rule. So I'm going to erase that awfulness. Okay. I'm going to make my pencil bigger. Okay. So to do this, you have to apply the product rule. And I would think about 6x as your f and y as your g. Your first function and second function. Okay, so how does product rule work? Differentiate the first. So the derivative of the first is 6, and the y doesn't get differentiated in that iteration, does it? And then add. What's the derivative of y? It would be 1, and then dy dx. So the only difference is the need to add that dy dx when what you're differentiating is a y. That's the only difference. Okay, and now you're like, okay, question said to find dy dx, and what the heck, Beth, or Ellen, how do you find dy dx? Okay. Remember when we had this question of finding the inverse of this rational function, and one of the tricks was to get all of the y's in the same side and factor them out? Does that kind of ring a bell? Like we found inverses of like x plus 1 over 2x minus 3. So that's the same trick here. Get everything that has a dy dx on the same side. So I'm going to put them all on the left. The things that have a dy dx are 3y squared dy dx minus 6x dy dx. On the other side goes all the stuff that does not have dy dx. So the 6y does not have dy dx. What else doesn't? Minus 3x squared. And I had to minus that to move it from the left side to the right side.
Could you take the dy dx out?
That's the whole purpose of doing this thing, is now because every single term on the left has a dy dx, you can factor it out. Okay. And then now can you get the dy dx all by itself? Divide by it, exactly. So dy dx equals 6y minus 3x squared over 3y squared minus 6x. Beware of bad cancellations and killing your kittens, for lack of a better way to say it, okay? I mean, it's just, might be silly maybe to remember. Can you take out a greatest common factor here at all? You could divide the numerator and denominator both by 3. Does that make sense? And that would make this into 2y minus x squared over y squared minus 2x. Okay. The kind of crazy thing, it's always going to work. This is not an equation in the get-go we could have solved for y, is it? There's no immediately obvious way to solve it for y, is there? No, it would be really challenging, and maybe not even possible. I don't know how to do it, so I'm not going to try. But even though you couldn't solve for y in the original expression, you could solve for the derivative. And this gives you slopes of tangent lines to things that aren't necessarily functions. Like if you graph this thing, it's not going to pass the vertical line test. It's not going to be a function. But you can still find slopes of tangent lines. The circle wasn't a function either, was it? No. So, okay. Now one more thing. You didn't have to get dy dx on the left. You could have gotten dy dx on the right. Does that make sense? Would your answer look different? It shouldn't be different, right? But it might look different. Now, here's what it would look like. It would look like x squared minus 2y over 2x minus y squared. So sometimes what might happen is if you choose to do a problem and put the dy dx on, say, the opposite side that I do, your answer will be just the opposite of it in both the numerator and denominator. See what I'm saying? Like multiply this numerator by -1, you get that, right? Multiply this denominator by -1, you get this. So this was a hard thing when I taught AP Calculus because my students took multiple choice tests. And if they happened to not do it the exact same way, they might get the opposite answer. In which case they had to pick out which one's the right one. Does that make sense? But for you guys, WebAssign is smart if it can catch both of them. But if you're checking answers in the back of the book or something for an odd numbered problem, just be aware that that might have happened. Okay, let's do another. All right, y cosine x equals x squared plus y squared. So what rule are you're going to have to use when you differentiate the y cosine of x? Product. Yep. Okay. So let's use the product rule. If you differentiate the y, you get 1 dy dx. The cosine x remains unchanged, right? Then what comes next? Y times negative sine x. Very good. Equals. Great. Yep, that's it. Okay, so that's cosine x dy dx minus y sine x equals 2x plus 2y dy dx. Okay. You didn't have to rewrite that, I just wanted to. Perfectionist tendencies. Do you have a preference for which side we get the dy dx on? I kind of like the left, it's just my thing. So if we put the dy dx on the left, you've got the cosine x, dy dx, who else is over there? And it will equal 2x, and who else has to go with the 2x? It'll be positive now, right? And then same step, take out the dy dx and divide, right? Exact same steps. Dy dx cosine x minus 2y equals 2x plus y sine x. or dy dx is 2x plus y sine x over cosine x minus 2y. So as long as you can recognize the fact that you add that dy dx and redifferentiate y, that really is this trickiest thing in this lesson. Other tricky things are like when to apply the product and when to apply the chain rule. Those are also a little bit tricky. But whenever you differentiate y, you add dy dx. And other than that, the getting the dy dx alone is always going to follow the same pattern. Get all the dy dx on the same side, factor it out, divide by it. Bam, done. Okay. All right, this guy. So this one is tricky because, I'll ask you, what rules and in which order do you have to use when you differentiate sine of that stuff? Plus the product. Because to take the derivative of the inside stuff, you're going to use the product rule on it. What's the derivative of a constant? 0. Even funny constants, right? So this will be 0 plus 1 equals. Okay, so for the chain rule, what's the derivative of a sine? Cosine. And you've got xy squared multiplied by the derivative of xy squared. I just didn't do it yet, but we have to do that part. And you've got to pretend for just a second that all you have to worry about now, which is actually true, is that xy squared's derivative. And that's going to involve the product rule. So 1 equals cosine of xy squared. Is this product rule going to expand into more than one term? So what do we need then? Parentheses. Patience and parentheses. Patience, product, and parentheses, all sorts of p's. Okay, so x's derivative will be 1 y squared plus then x times, great. It's not that bad, right? Just the whole add dy dx thing, that's tricky. Now, that dy dx is stuck inside of our parentheses. I think it would work best to just distribute. So 1 equals y squared cosine xy squared plus 2xy cosine xy squared dy dx. Does that make sense what happened? And now on your goal to get the dy dx by itself, what do you do first? Subtract the y squared cosine stuff, yep. So 1 minus y squared cosine of stuff. And then you can say dy dx equals, what's going to be your numerator?
1 minus y squared cosine stuff.
Cosine stuff, yep. All over.
2xy cosine stuff.
Exactly. If students make mistakes on this question, it is often one of two things. They do bad product rule, or they don't put parentheses. That typically is the mistakes that I see people make. I mean, I grade a lot of tests and things start to be common after a while, but that's two of the most common things. Yeah? You can't cancel the cos. So tell me why, because you answered your question. So the reason is because there isn't a cosine here. Yep. So nope, that's a kitten killing cancel. I'm just when you make bad cancels on tests, I'm just going to write kitten from now on, and you'll know what I mean. I don't believe in killing animals for, I'm just nuts, I'm just trying to make it memorable. Okay. This one is going to have the same sort of issues. So if you take the derivative of e to the xy, what rules is that going to use? Chain and product again. It'd be chain and quotient if it was x over y. Well, you could make that product by making it xy to the negative first. So what's the derivative of e to the stuff? E to the stuff. Got to multiply by the derivative of the stuff, which is x, y, and that's where the product rule comes up. And that will equal 1 plus 1 dy dx. Okay, e to the xy, what's the derivative of x times y going to be? 1. 1 times y. Plus x dy dx, right? Don't get, because the mistake is to say 1 dy dx. That's the bad product rule. That's the one you don't want to do because it doesn't work. It's not a rule. It's a non-rule. Equals 1 plus dy dx. Is that all right? It's quite similar, right, to the previous one. Okay, and then what would you do next? I would distribute, yep. Y e to the xy plus x e to the xy dy dx equals 1 plus dy dx. Is it okay if I get the dy dx's on the left? Okay. So x e to the xy dy dx minus dy dx equals 1 minus y e to the xy. Okay, and then the last thing is to factor out. And then divide. They all involve those last two steps, don't they, for the most part? Factor out and then divide. There you go. Is everyone okay with that part? The trickiest thing is when you have to apply the product rule, I think. I think that's the hardest part. So, okay. Well, this next one says find the second derivative. So which means find the first derivative and take the derivative again, right? Is that all right as an idea? Okay. So the first derivative is not so hard. Derivative of x squared plus 9y squared equals the derivative of 9. And the mistakes I see with stuff like this are silly. People forget the derivative of a constant is 0, and they say that the derivative is equal to 9. You just have to not lose your mind because you're in the middle of something else. So what's the derivative of x squared? And then we'll have plus. Yep. So this is 18y dy dx equals negative 2x, right? Or dy dx is negative 2x over 18y. You should always reduce your fractions because it's going to make your life easier. So what does this reduce to? Okay, so that's dy dx. It's kind of my fault, but I don't think we've discussed what this dy over dx notation looks like for second derivatives. I don't think I've told you, so I'll tell you now. It's not. It looks weird, but it's not super bad. So everyone's okay with the first derivative, right? Okay. So now we're gonna find the derivative of the first derivative, which is equal to the derivative of this. Okay. Say that again? That's a 9y in the bottom, yeah. Same as what it was above. So what this notation on the left becomes is it becomes d squared y over dx squared. They probably should have had this dx in parentheses in some sense, but dx is kind of like delta x, which is kind of like one name for something. But that's what this, and this notation means second derivative. If those little numbers were 3's, it would mean third derivative. Okay. What rule do you have to use in taking the derivative of that ratio? I can show you how to use the product. It's a little bit tricky, but I will show you. The quotient also works, but you can write it as negative x times 9y to the negative first. That is not going to work. Okay. Okay, well, let's finish this one on the chalkboard. I'm going to complain the summer sessions tomorrow. I don't know what else to do. I already did, but I'm not going to get a reply. And your class is now, and
You could display them afterwards.
yeah, I'll complain to them during the break that the smartness of the smart classroom doesn't work. I also got a friend who works for OIT, and I'll bother him. So, okay, all right. So we're taking the derivative of d squared y over dx. There is a light switch, or we can try 208, because that was when we're supposed to be in according to some musical classrooms. One more time. Let's go.
I'm sorry, that shock is just impossible.
Yeah, so hopefully there's nobody in there.
Everybody else have a machine? Okay. You need like the bright pink chalk.
Yeah, which I don't have because I didn't know I'd be forced to do a chalkboard.
Do it for the whiteboard in here.
Yeah, that would be like 21st century. You know, people are dinosaurs. Do you?
Not me, but
People, and we care about those people, right? I hate this classroom.
it's like the punishment.
I get to be on a stage. Woo!
Now when you jump and stomp the residents.
On some stage, it's misread.
Woo! I always wanted to be an actress. Not. Only if I'm discussing math, and that's a little silly. And then there's this computer in the way of my face, which is also annoying.
Can't you just move it out of the way?
Yeah, last time I touched that computer in this classroom, this thing stopped working. There's a reason I hate this classroom, is because I know that this doesn't always work in here.
Move the desks and wheel that podium over.
Okay, I don't want to fuss with the cables because it's the cables that occasionally were causing problems with my other class. I taught a statistics class in here last year in the fall, and it got so bad, like I would plan a lesson, have my iPad ready, and then the screen would wiggle. Success! Except for it looks stupid, but success, right? Can you see it?
Is this converting the HDMI to composite AV cables or something? This is
Probably, and so if you're really techie, how about you look at it like when we're done? I can maybe, all right. So on to the product rule. Okay. So what's the derivative of the negative x? Negative 1 times 9y to the negative first. Okay. And then plus negative x. The trickiest thing is differentiating that 9y to the negative first. So what's the derivative of, first you pull the power down, right? That becomes negative 1. What's the new power on the 9y? Negative 2. And then what do you have to multiply by? Almost. 9, and then a dy dx. Does that make sense? Why the 9? Because the derivative of 9y, if it were 9x, its derivative would be 9, right? But since it's 9y, it's 9 dy dx. I did it again. 9 dy dx. So negative 1 over 9y plus x over 9y squared times 9 dy dx. I got rid of the negatives, yep, because the negative and a negative makes positive. Okay.
Before I started doing this, I just pulled the negative 1 over 9 out and did.
Oh, that also works. Yep, that's a good strategy. Now what happens, does this make sense? Oh, you found us, okay. I thought you were somebody for some other class and I was gonna like have a heart attack. So negative 1 over 9y plus x over 9y squared dy dx. Do you see that what I did was I said there was that 9 squared in the bottom and I canceled it with the other 9 from the numerator? Yeah, okay. So now here is the tricky thing about this. You have your second derivative that involves dy dx. You actually know what dy dx is equal to. It's equal
What did you
to,
take away from the denominator?
this 9y squared means 9y times 9y. There I only have a single line, but it's because this really is 81 and that's 9, and 9 over 81 reduces to 1/9.
Oh, okay. No, that was a little tricky.
Yeah, that's a little tricky. Now, plug in what dy dx is. Plug in negative x over 9y. So this becomes negative 1 over 9y plus x over 9y squared times negative x over 9y.
So negative x squared over 81y cubed.
So negative 1 over 9y minus x squared over 81y cubed. Now, I'm completely fine with that as an answer as long as you get a common denominator. So what would you need to multiply by to get that common denominator? 9y squared. So we got negative 9y squared minus x squared over 81y cubed. There's one more tricky thing that WebAssign might make you do to get the answer correct. Take the negatives out. That's the first step. Okay, and here's my next step. So blow your minds. Negative 9 over 81y cubed. How the heck can I just say that 9y squared plus x squared is 9?
Because x squared plus y squared equals 1.
look at the equation you were given in the first place. Look at the equation you took the derivative of. You see? You were told that that stuff equaled 9, right? That last step is something that's tricky, and I'm not sure if WebAssign will make you do it to get the answer correct, okay? So I'm just warning you that this happens in all the problems that are kind of this form with the second derivatives, okay? So tricky thing number 1 is having to put in what the first derivative is. That's tricky thing number 1. Tricky thing number 2 is when you simplify, the numerator might actually be equal to some constant. And every problem I've seen and made up that's actually worked. So
Dirty.
that is dirty. So I'm just telling you that it's a possibility so that you can understand the dirty trick and be aware of it. So the question that says find the second derivative, just watch out. Okay? You can also see why it's kind of useful because taking the next derivative will now be really, really easy, won't it? Yeah. So,
Well, you wouldn't have been able to simplify that without that clever little trick. would you?
no, and if the numerator had not been 9y squared plus x squared, you couldn't do that. It's because that's what the original equation you had was. I'm not even sure why it happens in all of these cases, but it does happen for these second derivatives. So just be aware.
Will you be having us look like do the differentiate to like 1,000 or something like that?
Oh, no, probably not with stuff like this, because I don't know if there's any kind of concise pattern and it gets ugly. The ones where you do like the thousands derivative, there's definitely some kind of pattern that's easy to see. Okay, so one more. So if you have this equation, and g of 1 is 0, find g prime of 1. This isn't really all that different. It's just that instead of y's, you're given g of x's. Just take the derivative of it.
From the beginning, I just said g of x equals y, so like I could just,
Yeah, do you guys want to do that? Just do y equals g of x,
yeah.
like this? So then it becomes y plus x sine y equals 3x squared plus 1. Does that seem okay? And then it's just like the ones we just did, right? So take the derivative of both sides. It's going to be, so dy dx plus, what rule must be used on the x sine y? Product. So you've got 1 sine y plus x cosine y.
Y prime.
And you have to add a dy dx on that term because the variable inside the cosine was a y. Does that make sense? Okay. And then it's going to equal 6x. And actually, in this one, the dy dx's are already all on the same side, right? So you've got dy dx times 1 plus sine of y plus x cosine y equals 6x. That's annoying too. Or dy dx is 6x over 1 plus sine y plus x cosine y.
Because that one sine y all out of that side, it doesn't have a y prime in it.
Oh, shiznits. Yes, yes, yes. You guys, I'm so sorry. And my eraser works better than yours. So, yeah, erase. Or in the words of the Cybermen, delete. Anybody Doctor Who fan? Delete, delete. Yeah.
Anyway, so
Okay. So what has to happen to the sine y?
Subtract it.
Subtract it. Dy dx plus x cosine y dy dx equals 6x. So Jimmy, is the part that's bothering you? I bet I know what it is. Is this part?
what's that?
Is this part that got you lost?
No, there's so many things, just keep going.
Okay. So what can you do now on the left side?
Now you can factor this.
Now you can factor out that dy dx. Okay, and then you divide. Okay. And I'm just going to do one thing. This is g prime of x equals 6x minus sine g of x over 1 plus x cosine g of x. Do you see what I did there? Yeah, and because that's what, I mean, we are given information about g's, it might be easier if we just use g's in our notation, but that's just using the fact that since y is g of x, dy dx is just g prime, right? And regular y is just original g.
You think WebAssign needs you to put it back into that?
Well, WebAssign's looking for a numerical answer because you were asked to find g prime of 1. Does that make sense? And so, and I think, yes, if you were asked to find g prime of x, WebAssign would want you to use the g's and not the y's. It's kind of like how it makes you use the right variable. It doesn't like if you use thetas when the equation of x is in it, right? It won't count you right even if you're like really, really close. Okay, g prime of 1. So plug in 1. You got 6 minus sine of g of 1 over 1 plus 1 times cosine of g of 1. And I believe you were told what some of that stuff is.
G of 1 is 0.
Yeah, so 6 minus sine of 0 over 1 plus cosine of 0. One of those is not 0. Which one is not 0? The cosine. So that will be 6 over 2, or 3. It's not that different than the previous thing, though, is it? No. Okay.
But it's equal to 1, isn't it? Because g of 1 is 1.
Well, I think g of 1 is equal to...
No, g prime of 1. Like,
Why?
didn't you said it equal to 1?
Hold on a second. Did I make a boo-boo? No. It says find g prime of 1.
Oh, okay.
Like, what would g prime be when 1 was plugged in? Versus g prime of x equaled 1. Okay, yep. Great. Awesome. So one application of this implicit differentiation method is to get some different formulas for derivatives. So we're going to learn, I believe, 3 or 4 new formulas today for this section. But they're pretty close, they're related to each other, and they're all found in a very similar manner. So, inverse trig functions. We're only going to do inverse sine, inverse cosine, inverse tan. No inverse secant, whatever, those are stupid. Okay. So, I don't know how to find the derivative of this, but does it make sense that this is the same thing as sine of y equals x? Okay. Can you differentiate that using implicit differentiation? Yeah. So you'll have cosine of y dy dx equals 1. And so dy dx is 1 over cosine of y. So far, okay? Okay, and now the question is, how do you change cosine y back into x's? Because this formula will be useful if we can have a formula that tells us, okay, the derivative of sine inverse x is something that involves x's in it. And the trick is you use the Pythagorean identities. You say sine squared y plus cosine squared y equals 1. Okay? So then cosine squared y is 1 minus sine squared y. Make sense? And so cosine y is root 1 minus sine squared y. Technically that's plus or minus, but because this was positive, we know we're using a positive one of them. And I know that you might be thinking like, oh my god, that isn't actually helpful. So just plug that in instead. And here's the thing. What was sine of y equal to? X. 1 over the root 1 minus x squared. You don't have to prove this formula again, okay? What you have to know is that is the derivative of inverse sine, or arc sine. And it comes from this implicit differentiation idea. That last step where you do that substitution is definitely tricky. But if you just pointed out that that's what sine of y is equal to, it's not very hard to believe, right? Do you think finding cosine inverse's derivative is going to be super, super different? No, it's just you're just going to have cosine of y equals x, right? Then this would be negative sine y dy dx equals 1. This would become negative sine y. This would just involve cosines, and the formulas would be the exact same but negative. So it's kind of crazy. If you want to try something for yourself, you could try to do it with inverse cosine. It's going to be the exact, almost the exact same. It's just going to come out to be a negative 1 over root 1 minus x squared. Inverse tan's a teeny bit different. Okay, so you start with, first step would be to say tan y equals x, same as the other first step, right? So then you got secant squared y equals, oh, I missed something. Secant squared y times dy dx equals 1. And so dy dx is 1 over secant squared y. Okay. So can you change secant squared y somehow into things that involve tangents? 1 plus tangent squared y equals secant squared. That's the second Pythagorean entity, right? So 1 over 1 plus tan squared y. And why did I want to change it into tangents in the first place? Yeah, because tangent of y was equal to my x. That's why I wanted to go there in the first place. So what's that going to be? 1 over... Yep, and that one doesn't involve a root sign. So that's equal to the derivative of inverse tangent of x. And now we're just going to use them. Like, you're allowed to know that's what they are. You've proved them. You kind of understand where they come from. Now we're going to just use them to take derivatives of other functions. Okay. So this is just a summary. So the derivative of sine inverse is 1 over the root 1 minus x squared. On yours, that bar could be used as the fraction bar because yours is better than mine. That was my intention, but when I made it into a presentation, it just kind of got squished. Okay, cosine inverse will be the exact same as sine inverse except for it's negative. And if you want to prove to yourself that that's true, run through the thing that's just like sine inverse and just do it again. It's going to be very similar. And the derivative of inverse tan is 1 over... And so we're going to use these rules and find derivatives of functions that involve things like the chain rule and the product rule and stuff like that. Yes?
Do we need to memorize them?
These you have to memorize as well. Yep. So far the ones you have to have memorized are the 6 trig functions, e to the x, which you all already know, b to the x, right? So say 6 trig functions. There's the e to the x, which you pretty much know, right? B to the x, and then these 3 inverse trig. I think there will only be, I might be wrong, but I'm pretty sure that there's just 2 more formulas you have to know after that. So what's that, 11 so far?
That's 4 more.
There's 4 more? Okay. Oh, we already had e to the x and a to the x. Yep. Now, that would be it for the memorizing programs for the chapter. So it will take you probably 12 or 13 flashcards, which really isn't that many. Like,
Is that it for the chapter?
I took Russian classes. You know how many flashcards that took? Holy shiznits.
Probably the same as all the,
Any other language whatsoever. Yeah.
I did it for osteology, I had 7 days.
Yeah. I mean, and also, I speak random thought. Okay, random thought and I'll stop. I speak fluent Swedish. Totally random, okay? But when I was in Swedish classes in college, like I had boxes of flashcards. Like it was insane. You don't realize how many words you know until you try to learn a foreign language. Like, oh, there's so much. Okay, so moving on. So y prime. So I have cosine inverse of something, which means you have to use what rule? The chain rule. So the derivative of just cosine inverse of x is negative 1 over root 1 minus x squared. In this case, what goes in for x? 3x plus 5. So I'll have negative 1 over the root 1 minus 3x plus 5 squared times what from the chain rule? Times the derivative of 3x plus 5, which is almost 3. So y prime is negative 3 over the root 1 minus 3x plus 5 squared. You could square that out, distribute negative combined like terms. I mostly care that you get how to use the chain rule. So in other words, the derivative of cosine inverse of stuff is negative 1 root 1 minus stuff squared. Some textbooks, to make it easier for you, they use u's instead of x's in the formulas because then you think, okay, whatever u is, that's what gets plugged in for that spot. And then they'll even add on times u prime, which is like forcing you to remember that that's a chain rule happening. Okay, this one. So who's the inside function? Arctan. So the squared is the outside function, right? So the y prime will be 2 arc tan of x to the first times the derivative of arctan. So what's the derivative of arctan?
1 over x squared?
1 over 1 plus
1
x,
plus x squared?
or x squared plus 1, same diff, right? So that ends up being 2 arc tan x over 1 plus x squared. Does that make sense? Okay, great. Alrighty, what rules is this bad boy gonna use? And chain. Alright, so y prime will be 2x tan inverse of root x plus x squared times 1 over 1 plus root x squared. Does that make sense? Times the derivative of,
Oh, she took the whole thing.
because you took the whole inside thing, right? Times the derivative of root x, which I still have to do. If you can do it in one step, you're good to go, but I'm just making sure it's clear there's the chaining part. Okay, so simplifying slightly, that's 2x tan inverse of root x plus x squared over 1 plus x, right? Now what's the derivative of root x? It's 1/2, right? X to the new power of
You did 2?
almost negative 1/2. Because it's 1/2 minus 1, right?
Yeah.
Okay. Which if you're going to write this simplified as a denominator, just be a little bit careful. I'm going to make a mistake on purpose. what should I have there? It's always the same answer. Should have parentheses. But the reason is, like the thought bubble is that this piece right there is 1 over 2 root x, right? If you do a fraction times a fraction, the numerators multiply, the denominators multiply, right? And that's what it would look like. It doesn't matter what order this is in, it's just that the denominator includes both 2 root x and the 1 plus x squared. You could also distribute it if you wanted to, like it doesn't matter.
Where'd you get the 1 plus x squared?
Oh, shoot. I didn't. That was a mistake I didn't make on purpose. What should it have said? Just 1 plus x. I'm so sorry. That's why I make mistakes and you ask questions. Actually, I make mistakes because it happens, but, you know, helps that you ask questions. Okay. On this kind of crap, don't get a common denominator. Okay, like, I'll ask for it specifically if I want it. Like, and I'm probably going to use the word simplify. That means get a common denominator. If I don't say simplify, just like, it's good enough.
So if it's,
If I want a common denominator, I'll say get a common denominator. Because I do want it sometimes to make sure that you can do it, but I don't need it for stuff like this. Okay. So this one involves 2 bits. This first bit, well, it must be in white. Can't see that. This first bit involves the product rule. Does that make sense? What does differentiating this bit need? Chain. Good. So y prime is 1 sine inverse of x. Does that make sense? Plus x times what? Great. Okay, so I'll just try to color code. That's the derivative of this part. Okay? Now the next part is this guy. So what's the outside function there? The square root, which is a power of 1/2. So we'll have plus a half stuff to the times, which is negative 2x. Great. Okay, so that's sine inverse x plus x over the root 1 minus x squared minus x over the root 1 minus x squared. What happened to the 2's? It's just sine inverse of x. Sometimes those problems simplify down quite nicely as long as you do them correctly. It wouldn't do that if you didn't take the tuning book correctly. But yeah, that will happen with some of your homework questions, so don't be freaked out when it does. I'm glad you figured it out. I have a note packet. There you go. Thank you. Okay. This is the last one, right? Find all points on the curve where the tangent line has a slope line. We've done this, but we haven't done slope one. We've often asked where the tangent line is horizontal, which means the slope is 0, right? So what we're going to have to do here is we're going to find dy dx, and we're going to figure out when does that equal 1. Okay, we're going to figure out when that happens. We'll be able to get points from that once we know it. Does that make sense? But tangent line having slope 1 means the derivative is 1. So we're saying when is the derivative 1?
so is that all equals 1?
After you found the derivative. Yep. So first step is then find the derivative. So this derivative isn't super hard, is it? It's going to be 2x plus what? Then dy dx equals 0. So 4y dy dx will equal negative 2x and dy dx will equal negative 2x over 4y, or it's negative x, don't know why I just wrote squared, negative x over 2y, right? Okay, then what do we set that equal to? 1. Might be feeling slightly cheated because it doesn't give you anything right away, does it? It's the same thing as saying, though, 2y equals negative x, or x equals negative 2y, isn't it? And then you can use that information here by inputting it. So you'd have negative 2y quantity squared plus 2y squared equals 1. I think that's 4y squared plus 2y squared is 1. That method's called substitution, where you replace something by something else. So what's 4y squared plus 2y squared?
6.
And y squared is 1/6. So y is plus or minus the square root of 1/6. So just a disgusting ugly number. So in the event that y is positive root 1/6, can you use this equation to tell me the x coordinate there?
Yeah.
It should be negative twice that, right? So negative 2, can I just say negative 2 over root 6? Because technically this is just plus or minus 1 over root 6, isn't it? Because 1's square root is 1. Okay, there's 1 point. What if the y coordinate was the negative 1 over root 6? What's the x coordinate going to be then? It'll be positive or negative? It'll be positive 2 over root 6. So what will happen with this kind of question, which you're going to get, is you're going to get an equation that they'll have both x's and y's, and you're going to use it with the original to get rid of one of the variables. And that's called substitution, which you probably learned in a previous class, hopefully, maybe. I know I taught it in my pre-calc class, so. Okay, awesome. That is it for this lesson, right? Okay, so let's take a break.